So we talk about on Tuesday the three methods, right, to solve for the zeros of a potential nonlinear function, and they all came from a simple theorem in calculus, which I explained, I hope hopefully well, by a picture, right? Think of that picture. If you forget about what's going on, right? So in particular, we're talking about that. We'll talk about that. We have the k plus 1's iterate, all right, is given by the k's iterate, right, minus f at xk divided by something, all right. That something, this something should approximate f prime c for some c, which calculus told us it exists, but we just don't know where it is for any given function. All right, for some c between xk and xk plus 1. All right. So what is this? Is that, like, if you're confused about, hey, we're going from xk to xk plus 1, so it must be in the form of xk plus 1 equals something in terms of xk, because remember the goal of this step is the iteration, is to go from xk to xk plus 1, right? So the left-hand side should have no confusion. Is it clear? So equals xk, and then is it plus or minus, or is it, and then later on is it division or multiplication? Think of this in the other form. Remember, we solve for this. We solve for this from the little theorem, right? So if you're confused and when you code things up, it's always a great habit to write them down on paper, a formula down. You know what you should code, and then code it up, right? So you need to either have this formula in your mind when you code things up, or have it on paper, right? So the way I would think of this, if I'm not sure, is that this is equivalent with what? With the original form where we solve for xk plus 1 is, well, this something times xk plus 1 minus xk, right, is equal to 0 minus fxk. They are the same form. So the 0 here, the 0 is at f xk plus 1. That's your goal. The goal here is to make the greedy goal, right? You're hoping in one step you get to a solution. So which means what we're having here is that, well, that something is equal to f xk plus 1. I'm repeating myself from last class, right? F xk, because this is so important. This is yet a third form of this equality. Now this should be clear, because this equation is a slope, right? It's f at one point minus f at the second point divided by the first point minus second point. So that's slope. And I hope everyone recognize that. If you don't, then I'm in trouble, right? That's a slope. That's the slope of the line connecting the 2 points. So slope, remember the picture, we shift the slope, the line, right? So that it is tangent with a curve. So this slope is equal to some f prime. Okay? So they all have this form. They all have this form. In particular, we have the called secant Newton, but here is the secant, and because that's something we will look into a little more today. Minus, we take that something to be the slope approximated by the last two iterates. All right, the slope that something is on the bottom on the denominator, so we flip it, we get what? Xk minus xk minus 1 divided by f xk minus f xk minus 1. This whole that's 1 over something, right? This guy. Okay, this guy. And as announced last time, today we're going to compute, we're going to prove, we're going to show that the convergence order P, right? Convergence order P. We talked about the convergence order last time. We showed that if a scheme has order 2, it's actually, very fast. Every step, the error gets squared, right? You have 2 digits. Next step, you have 4 digits. Okay, this is convergence order. For that, we need to study we define the error. Right? I'm going to use epsilon k to denote it. Is the k iterate minus alpha. Alpha is exact solution, right? So the question then for the order question is then recall we talked about last time is this absolute value xk the next iterate, the error at the next iterate, is this less than some constant times the error on the current iterate to some piece power, right, asymptotically. So in pre-calculus, actually, if you plot, say 1 over x, the graph, we talk about asymptotes, right? So asymptotically, it behaves like what, right? The asymptotic behavior, which means when k is large enough, it goes on. Toward the end, you have this behavior. 1 over x, when x is huge, it approaches the x-axis. That's asymptotes. Is that clear? That's the concept of asymptotics, right? Think of 1 over x, the asymptotes. All right? Which means, asymptotic behavior is something towards the limit when k is large. That's why we had this k0 when k is larger than k0. This is not true when in the earlier steps, but towards the end, the scheme exhibits such behavior. Okay, each time you go one more step, the error gets squared. If p were 2, we of course don't know. We just need to find out this p, right? I'm going to do this. This is harder than the other case, which I'm going to leave as homework for the Newton's scheme. We're going to do this for the secant. You can get the idea. All right. So the tool, as we were saying, just the Taylor series. We reviewed that, and that's pretty much the tool we use all the time, right? So make sure you can do Taylor expansion while you're sleeping. That's how well you should know it, all right? So what we're having is, remember, this is our scheme, right? This is a scheme. We need to study the epsilon, the error. So if I subtract both sides of the equation by alpha, I get epsilon k plus 1, right? If I just subtract by both sides by alpha, is equal to epsilon k minus, I have xk minus 1. That's same thing as epsilon k minus epsilon k minus 1. Because they each has minus alpha in it. They cancel with each other. Divided by fxk minus fxk minus 1 times fxk. This equation is coming from that equation. Let me explain more. So what's next is, again, the goal is try to write everything in terms of epsilon k, right? Because that's a quantity we need to study. And the next is the Taylor expansion. The f of xk, right? F of xk. Now we expand the function around alpha. So this is equal to f of alpha, the first term, plus f prime alpha times alpha is our base now, right? We go from alpha to xk times what? So it's xk minus alpha. That h is x plus h minus x. You start from your base, you go from your current point, right? And but we know xk minus alpha in terms of epsilon. What is it? Epsilon k, right? Epsilon k plus f prime alpha over 2 factorial times that h squared, epsilon k squared. All right, and another way of, we write it down in the infinite series. We provided the remainder. Another way that the z comes in. The third way is, if you don't keep writing, one way is write, okay, what we're ignoring is smaller than the little o of epsilon k squared, means whatever we're not writing is smaller than xk squared, because the leading term that we're ignoring is xk cubed, and then epsilon k to the fourth, and so on and so forth. This again should be in the calculus book, but I'm not sure if it was covered at the time you were taking. So what that is that whatever that's covered in that term, all right, if you divide it by epsilon k squared, it will go to 0. So it's infinitesimal comparing with that epsilon k squared. Yes. That's right. Oops. Is that what you want? Yeah. All right. But we know f of alpha. What is f of alpha? What is f of alpha? 0. Right? Alpha is our exact solution. 0. So this is, because this guy is 0, and this is epsilon k times, I'm going to write it this way, f prime alpha plus times 1 plus, because I'm going to factor out epsilon k f prime, 1 plus f double prime alpha divided by 2 f prime alpha epsilon k is approximately equal to that. We will ignore the high order smaller terms. All right, I'm just factoring out epsilon k f prime alpha. And moreover, I don't want to keep writing that term. I'm going to call that a. So we are having epsilon k f prime alpha times 1 plus a epsilon k. So now everything is in terms of alpha or epsilon k, and epsilon k is something we need to observe. right? I'm just denoted by A. That's it. A is in terms of f and alpha. We need to keep that in mind. It has no epsilon in it. This is f of xk. If we were to do the whole thing again for xk minus 1, all right, what would you get? So that is equal to epsilon, as we just discussed, f prime alpha times 1 plus a epsilon k minus 1. All right? If you put these two equations, number 1, number 2, into the star, right? We put number 1, number 2 into star. What do we get? We get epsilon k plus 1 is equal to epsilon k. Right? Minus, we have that epsilon k minus epsilon k minus 1 on top times fxk divided by fxk minus f of xk minus 1, right? Which we now know. That's epsilon k f prime alpha 1 plus a epsilon k, right, divided by the difference of the two. Right, the difference between 1 and 2. So I'm going to do a little bit of rewriting here. So this is this minus that, right? The difference of the two. So the first term is f prime alpha times epsilon k minus epsilon k minus 1. The second term is a f prime times epsilon k squared, right? So that's a f prime alpha times epsilon k squared minus epsilon k minus 1 squared. Let me explain. So what do we do next is we simplify this in a way we can figure out the p, the order p. First of all, we can cancel the f prime, right? Because both terms below has f prime. And the next is I'm going to cancel epsilon k minus 1. But that's not so trivial. Anyway, I'm expecting you can do it. So this is epsilon k plus 1 is equal to epsilon k minus what we have on top is 1 plus a epsilon k. What we have on bottom after cancel epsilon k minus 1 is 1, right? 1 plus a times what? So again, that's a plus b, a square minus b square over a minus b, you get a plus b. So that's epsilon k plus epsilon k minus 1. All right? You further simplify this and write it in one quotient. Epsilon, the same denominator, common denominator. And you have, let's do it in 2 steps. You multiply epsilon k, right? Epsilon k plus a epsilon k plus epsilon k minus 1. This same thing times epsilon k minus 1 minus a epsilon k, right? All right. What is this? We had type above. So that what we had above is epsilon k multiply. That's epsilon k multiply 1 plus a epsilon k. So that's epsilon k squared. So that was type epsilon k squared. We're going to have the square. All right, now it makes sense because we can cancel this guy with that guy, right? Because they're both giving me a epsilon k squared. All right, and the 1 is not 1 anymore, right? That's another typo. So there is epsilon k. 1, it should be epsilon k, and here 1 is epsilon k, right? Because we didn't. That's error from last step. So epsilon k would cancel with epsilon k. All we have left is a epsilon k minus 1 divided by 1 plus a epsilon k plus epsilon k minus 1. Beautiful. Let's work this out. So remember, what do we need to figure out p, right? So need to figure out p. What is p? P is like my epsilon k plus 1 is kind of like, remember that asymptotic meaning is they have the same order. So epsilon k plus 1 is like epsilon k to the pth power, right? Approximately equal to. And again, this is asymptotic, so k is large. When k is large, k minus 1 is also large. So we expect similar things for epsilon k. And epsilon k is at the order of epsilon what to the p. So k minus 1 to the p. All right? So that means what we had above, epsilon k plus 1 is a epsilon k minus 1, 1 plus a epsilon k plus epsilon k minus 1, right? This is to say, because epsilon k plus 1 is this is not completely rigorous, so this is kind of like c times epsilon k to the p is equal to so we get rid of that k plus 1 term, is equal to a epsilon k minus 1 divided by 1 plus a epsilon k plus epsilon k minus 1, right? Which means that if we cancel the epsilon k from the right, we're going to get epsilon k to the p minus 1 is equal to, I'm going to put the constants together. A is like constant, right? A, remember, is in terms of f and alpha. So I'm going to move c to the right hand side, right? What I have then is epsilon k minus 1 divided by 1 plus a epsilon k plus epsilon k minus 1. All right. Okay. So what we're doing next is keep doing things like this. Is ignoring the high order term. In comparison to 1, right here we have 1 plus that. Epsilons are small, the error. A is a constant. So this is kind of like 1 plus constant times a really tiny number, right? And this is like epsilon k to the p minus 1 is equal to a over c, right, times epsilon k minus 1 divided by 1, because comparing with 1, that's tiny. The a times 2 epsilon is tiny. All right. So which means, what does that mean? That means I can solve for the epsilon k in terms of epsilon k minus 1. So my epsilon k is equal to the right hand side to the what? To just take 1 over p minus 1 power, right? So this is a over c to the 1 over p minus c times p minus 1 times epsilon k minus 1 to the 1 over p minus 1, right? P minus 1. So which means, on one hand, you're telling me by the definition, epsilon k should behave like that. Is k is epsilon k minus 1 to the p. On the other hand, it should behave like that. The constant doesn't really matter. What matters is the power. Right? It's x squared or x cubed. So which means they must be, I mean, they talk about the same thing. They must be equal. They must be identical. So which means P is equal to what? So P is equal to 1 over P minus 1, which we can solve because that's P squared minus P minus 1 is equal to 0. So P is quadratic formula, right? Quadratic formula. 2a negative b plus minus square root of b squared minus 4ac, which is 5. Right, 5. And which one should we take? We take the positive guy. And that's so that's roughly square root of 5 is like 2 point something, 2.2 something, right? Just have some idea. So this is roughly 1.6. 2.2 plus 1, 3.2 divided by 2. Right? So it's not as fast as 2. So each times error gets to the power 1.6. Not as fast as we're talking about from 2 digits to 4 digits, but that's pretty fast actually. If you compute it, you raise a small number to the 1 plus 6 power, you'll see. Questions? So if you want to, that's something that I will ask you to do in the homework. If you want to numerically verify the order, right? How do you do it? How to do it? All right. So this is because we're going to use this kind of trick later on as well. So I'm trying to explain this. You either use a function that's given in the problem, or you create your own function, some function that you know is 0, right? So you know the exact solution alpha. We're just testing the scheme, so that's okay. Yeah, that's not cheating, right? We're testing this manufactured test case. So we find f of x, some function, such that you know alpha, f of alpha is equal to 0. You know its root, so you know the exact alpha, okay? And then you apply some scheme, apply the scheme, either bisection or chord or secant, whatever, right? You're going with the initial guess. Epsilon 0. Of course, you better not choose that to be alpha, even though you know alpha, right? It's okay. So start away from alpha. And then you have your x1. You get your x1, x2, and so on and so forth, right? So on and so forth. And then because you know alpha, again, this is a test case. You know alpha, so you can compute the epsilon, right? Epsilon k to be that x k is iterate minus alpha, right? Minus alpha. And the next step is you can figure out that p. Figure out that p. There's a trick here that's used often in numerical schemes, numerical analysis. Is course in the next semester as well. We essentially have this kind of law, right? It's a power law. So we have epsilon k plus 1 is like c times epsilon k to the power p, right? Power p. Okay, power p. All right. How do we reveal the p? That's a trick, right? So if you take logarithm of both sides, so you're going to get a log epsilon k plus 1 is like log c plus log epsilon k minus 1 times, what do we put p? Times p, right? Times p. So p becomes a slope, you see, by taking the logarithm of both sides. This is called log. You do log of both sides. And sometimes when later on, when it's exponential, we do so-called semi-log. If you do log on one side, the convergence order becomes a slope. So p is not a power anymore. That's easy for you to observe. So for example, you can so if you make a table, for example, you can compute. If you compute log epsilon k plus 1 minus log epsilon k divided by log epsilon k minus log epsilon k minus 1, right? K minus 1. That will be the p. Okay? I mean, there was a typo there. It's just k. All right. Or you can simply plot this. Every time you get log, plot this in terms of k. But play with it and you can compute this p. Questions? Log epsilon k plus 1 minus p log epsilon k. This is equal to log epsilon k minus p log epsilon k minus 1. So this means log epsilon k plus 1 minus log epsilon k is equal to p times log epsilon k minus log epsilon k minus 1, right? K minus 1. Right? So that way you can, as you proceed, of course you don't have an order for the first number or even the second if you compute this case, right? Then from third on you can compute this ratio. That's your p. It's not likely to be that 1 plus square root of 5 over 2 in the beginning, but you should asymptotically approach it. If it were 2, you're going to get something closer and closer to 2. Any other questions? So the next part is we're going to do some so-called fixed point iteration. This is essentially the same as what we're doing, just a different framework. There's a lot of benefit for taking that framework, but we're going to elaborate later, right? So recall what we have. Recall what the schemes that the last 3 schemes all have the following form, right? Epsilon x k plus 1 is equal to, for example, for Newton's, minus x k. We just did secant. Let's take Newton's example to review the third scheme. The something, STH something, we use f. It should be f prime c, but we don't know c. We use f prime xk, right? All right. So if you look at this is the right hand side is a function of xk. You plug in xk to the right hand side, to the function of the right hand side, you get xk plus 1. This is in the form of xk plus 1 the form of xk plus 1 is equal to some phi of xk. With the function phi of x defined to be x minus f of x divided by f prime x. So what we observed, all right? What we observed is that solving. I'm going to give another simple example. Solving f of x is equal to 0. All right, is equal to 0. Solving for some roots or zeros of a nonlinear equation. This is equivalent, right? This is equivalent sign, equivalent to solving x is equal to phi of x for some phi corresponding to f, of course, corresponding to f. You can always do this. What the scheme we did happens to be that form. That's a advanced scheme. But if we go back to the basic function, you can do that as well, right? If you go back to the more basic cases, say if I want to solve x squared minus 2x plus 1 equals 0. Right, equals 0. Then this is of course the same as x squared minus. One thing I can do is I can add x to both sides. So that becomes, if I add x, is minus x plus 1 is equal to x. So i.e. for that phi is equal to x squared minus x plus 1. Right? That's our f. And which means this f corresponds to that phi. We can always do that. The simplest way you just add x to both sides. Right? Just different way of raising the same question. Then we talk about the advantages and disadvantages of different way to choose this phi. But you can think of this as what is it? Another way is this can easily be rewritten differently. Say I might have is x minus times x minus 2 plus 1 is equal to 0, right? So this is x is equal to 1 over 2 minus x. Right? I move 1 to the other side. I divided both sides by x of minus 2. So in this case, the phi now, a new phi is 1 over 2 minus x. Right. Just an example, so that's achievable. You always find a phi for that purpose. And this is a very special case, a special meaning, in the sense that they now all have that form. It's in the form of x is equal to phi of x, right? The solution to that equation is called a fixed point. This is where the fixed point comes in. Fixed point. So the point is fixed. You plug in x, you get x. Does that make sense? That's called fixed point. Fixed point because you put x into phi. If x is the exact solution, you get x. It doesn't change. A phi is like action. You act on x, you get x back. Okay, and the phi for the Newton's method is that particular phi above. So this is the phi for Newton's for f. This is 1 prime, and this is of course complicated than a simple algebraic functions. That's you have a phi for any f, right? F prime. Is that clear, the idea? You go from solving an equation to be 0, change it to solve for the fixed point. You have a phi. The only thing now we need to do is to find a fixed point. It doesn't move. All right? Let's talk about a very important theorem. THM means theorem. All right. If this phi is function from A to B to A to B, right? If that's the case, phi is function. This is the way you write your domain range. Phi goes from the domain is A to B. The range is also A to B, right? If this function is continuously differentiable, how many of you know what that means? What continuously differentiable means? All right. That means its derivative is continuous. A function can be continuous, and its derivative might not be continuous. You have a kink. X epsilon value is continuous at 0 at the origin, but its derivative has a jump. So we're ruling those out. If its derivative is continuous, and there exists k, some k, large k, capital K is less than 1, such that if you take the derivative, not only is it continuous, but also its absolute value is less than k for all x in AB. right? In AB. Okay, in AB. Then, if that condition is satisfied, then there is a unique solution, alpha, such that to the fixed point problem, which is phi alpha is equal to alpha, which is f of alpha is equal to 0, right? And moreover, if that's true for any initial guess, epsilon 0. That's wonderful, right? Because you can start anywhere. You're going to get to the solution. So this thing is called contraction. As we prove this, I'm not going to talk about a lot of theorems. This is the one theorem that I think we should talk about, and moreover, we should talk about its proof. You'll see what contraction means, right? We're going to do very few theorems in the class. All right. So again, we're going to prove this. The proof is not the point. The point is, as we do the proof, we're reviewing a lot of things, which are important, including things we just talked about last week. All right. So the conclusion, you have an assumption, you have a conclusion. Proof is go from assumption to conclusion, right? The conclusion is that there exists solution, and the solution is unique. That's three things. There exists one, that's a unique one, and then it is true for any initial guess. It's a very strong statement, right? You can start anywhere, mathematically guaranteed to converge. Okay, so you need to be careful, what you need to prove. The existence is trivial if you remember what we did in the first class. Is the existence, that exists solution. Otherwise we'll talk about empty set, right? You first make sure there is otherwise you're what are you solving, right? You need to talk about existence. That can be interesting analogies if you don't want to chase somebody that doesn't exist, right? The existence is trivial because if you look at phi, the domain is A to B, the range is A to B, or it can be a subset, and it's continuous, and continuous. I can stop there. I hope you understand. That's we will talk about if you look at if you. So maybe I should really be more. So phi A is less than A. Phi A is larger than A because the range is in AB. So phi A should be larger than or equal to A. But if it's equal to A, we're done, right? There exists solution already. A is a solution. So that's trivial. So we assume phi A is larger than A. Otherwise, we're done. And phi B is what? Less than B. Otherwise, we're done also, right? So this means if you look at the function g of x, which is phi of x minus x, we know g of A is larger than 0, and g of B is less than 0, right? By the what theorem? The theorem that we derive from the bisection, right? It's the one end is larger than 0, the other end is less than 0. There's opposite sign. There must be a 0 in the middle, right? The intermediate value theorem. So we know there must be a solution. Uniqueness is also easy. there exists a unique solution, right? Uniqueness. So there's also the typical type of proof. If you this should be like what's that? At 181, 182, a typical type of argument. If you want to prove something is unique, you prove by contradiction, most likely, right? You assume it's not unique, and then you conclude with something crazy, which must mean your assumption is wrong, right? That's how the proof of contradiction goes. So, if there are alpha 1 and alpha 2, they're not equal, otherwise it's unique, right? And they're both solutions, right? And they both satisfy that phi of alpha 1 is alpha 1, alpha I is alpha I is 1 to 2, right? They're both solution to the fixed point problem. So then if you subtract both equations, I'm going to get alpha 2 minus alpha 1. We know alpha 2 is phi of alpha 2. Alpha 1 is phi of alpha 1, because you're telling me those are solutions, right? Phi of alpha 1, phi of alpha 2. We prove this, and then we're done for today. Alpha 2, because it's a fixed point, you're telling me there are two solutions. So alpha 2 is equal to phi of alpha 2, right? That's a trick. We replace alpha 2 by phi of alpha 2. Now this is what? This is something, if I leave a box here, this is something times alpha 2 minus alpha 1. What is it? Phi what? Remember, alpha 1, alpha 2.
Greek square root thing.
Yes.
Yeah.
But I want you to tell it's phi what? Is it phi or phi double prime or phi what? 1 prime, right? It's a derivative at some c, at some unknown c, between alpha 1 and alpha 2, which is of course between A and B. Right? So we're going to get something crazy, a contradiction, because if you take absolute value of both sides, you're telling me this is absolute value of phi prime at some c on the domain times alpha 2 minus alpha 1 absolute value. And this is less than, by assumption, this is less than k, right? K is less than 1 times alpha 2 minus alpha 1, and we know k is less than 1. So you're telling me alpha 2 minus alpha 1 is less than alpha 2 minus alpha 1. That's crazy. So the assumption is wrong, right? So there is a unique solution. So next class we're going to continue this and show you what do we mean by contraction.